Hi guys, this is video Unit 1, Day 6. You're supposed to be watching this on Thursday 9:15. Okay. So I'll see how long this video takes and then I'll adjust the homework accordingly. This is on page 12 in your video packet, the green packet. Variations of the following limits are going to come up a lot. Now there's a space here because I originally had plus or minus, because this could be positive or negative infinity. Okay, so the limit as x approaches positive or negative infinity of a over x to the n. A and n could be any, well, a could be any number. N could be, yeah, a and n both could be any number. So here's some examples of functions like that. For example, 2 over x to the 5th. So a is 2, x is 5. Or no, n is 5. You could have 1 over x. There a would be 1, and also n would be 1. And just one more, 7 over x to the 2nd. Okay? Now, yeah, so we'll do this one first and then I'll talk about the other one. The other one is just like the reciprocal situation. But if x is getting bigger and bigger and our function is a over x to the n, then the question is what's happening to y? It's the function value. Okay, so let's take let's take this one and see what happens as x gets bigger and bigger. All right, so here's my calculator. So, let's start with 7 over, our function is 7 over x squared. So let's start with 7 over 10 squared. 0.07, that's a pretty small number. Let's see what happens when I plug in an even bigger number for x. 7 over 100 squared. It gets even smaller. This on the calculator means 7 times 10 to the negative 4th. That's a very, very small number. It's like 0.00007. And as you can imagine, as x is getting bigger, the output is getting smaller. So the y's are getting closer and closer to 0. So if you have a situation like this, where the denominator is outgrowing the numerator, the y values are going to approach 0. All right, now the reverse situation over here. This one comes up, I don't know, kind of less, I think. Maybe that's not true, but, all right, so over here, these would be examples of this situation. All right, and let's see what's happening. I'll take the same, corresponding function. All right, and this time, for example, 10 squared over 7. Okay, 14 point something. 100 squared over 7. Much bigger number. 1,000 squared over 7. A much bigger number, and it's growing fast. So, as the x's are getting bigger and bigger here, the output, the y values are also getting bigger and bigger, going to infinity. And it could be positive or negative infinity depending on whether a is positive or negative, or whether n is even or odd. Okay, and it'd be a good exercise to think about why what I just said is true. Okay, so that's infinity. I'm going to start just doing 2 circles, guys. Doing the sideways 8 is sometimes a struggle for me. Okay, so there's that. Okay, now that we have that out of the way, we're going to do a few examples here using what is called the end behavior model. All right, and the end behavior model works like this. If the x's are getting, or if the x's are approaching positive or negative infinity, then what is determining the end behavior, meaning the behavior of the function way far out at positive or negative infinity, is going to be the terms with the highest exponent. Okay, we could talk about in class why this is true, or you could just Google end behavior model or something if it's hard for you to wrap your mind around that. But I'm just going to go fast because these are the video notes, and then we can talk about in class why it works this way. Okay. All right, so when you're dealing with a rational function like this, and you're finding the limit as x approaches positive or negative infinity, we're going to use the end behavior model. All right, so I'm going to think about the numerator. I've got two terms in the numerator, and which term is growing faster? It's going to be the one with the higher exponent. So that's the term that is determining the end behavior of the numerator. And then I look at the denominator. Which of these two terms in the denominator is growing faster? And it's that one. So these are the terms that are determining the end behavior, the behavior way out at positive or negative infinity of the function that we're working with. So guys, the limit as x approaches negative infinity of this function is going to be the same as the limit as x approaches negative infinity of the end behavior model. Okay, now this is important, guys, that these did not cancel. I'm just making the observation that these highest power terms are the ones determining the behavior of this function way out at negative infinity. Okay, all right, well this, now I can simplify, and I'm dealing with negative 3 over x to the third, all right? And now, this is looking like the first common situation that we have, where in this case, a would be negative 3 and n would be 3. All right, so I'm imagining plugging in some very big negative numbers for x, like negative 100, negative 1,000, negative 10,000, negative 900,000 or something like that. So so this denominator is growing really, really fast, but negatively. Okay, so I'm plugging in negative numbers, I'm cubing them so they're coming out negative, but really, really big. So, all right, let me do this if you can't. All right, some of you might know what it's going. Well, actually, never mind. Okay, so this numerator is staying negative 3. The denominator is getting huge but negative. Okay, so I'm approaching a very, very small negative number, which is getting small, or no, it'd be positive, because it'd be negative over negative. Okay, anyway, I'm approaching 0. All right. If that does not make sense to you, get your calculator out and start plugging in some very, very big negative numbers for x, and you will see how I got that. Okay, guys, example number 2, end behavior model again. This time the limit as x approaches positive infinity of negative x to the 5th over x minus 1. Well, in the numerator, I've only got one term anyway. Okay, so in my numerator, that's the term that is determining the end behavior, where x is way out at positive infinity. And then in the denominator, I've got two terms. The one with the highest power is x. All right, so this is the limit as x is approaching infinity of the end behavior model. I'm going to simplify. The limit as x approaches positive infinity of negative x to the 4th. All right. And I'm plugging in huge numbers for x, raising it to the 4th power. Positive huge numbers for x raised to the 4th power, but then I've got this negative out front. So this is just, this limit does not exist. Okay. Oh, sorry. This limit does not exist, but I'm going to be even more specific. This limit is negative infinity. All right. As x is approaching positive infinity, the y values are approaching negative infinity. Okay, guys, so there's that. Okay, so far this is a 9-minute video. I think I've got time to keep going. All right. The end behavior model, guys, also works inside of other functions. So here I have a composition of functions. I'm doing the limit as x approaches positive infinity of tangent of this inner function there, okay? And the end behavior model, if I did not have the tangent there, I could use the end behavior model, which works when x is approaching positive or negative infinity, only works then. I don't think I was clear about that. I could use the end behavior model on this, okay? This is where all the change is happening. So I'm going to go off to the side, all right? I'm not going to deal with this just yet. I'm going to go off to the side, and I'm going to say to myself, well, let me consider the limit as x approaches infinity of the inside function. Okay, that's the function that is inside of the tangent function. And this one I can use the end behavior model for. Okay, I'm going to work vertically here, guys. So end behavior model says that these highest power terms are the ones determining the behavior way far out at huge numbers. Okay, so this is the limit as x approaches infinity, 5x to the third over x to the fourth. This is the same as the limit as x approaches infinity of 5 over x. And guys, as we observed on the front page, so the numerator is staying 5, the denominator is growing huge, and as it gets bigger and bigger, this number gets smaller and smaller. So as the x's are going to infinity, the y's are going to 0. So now, that was like an aside, all right? So this is aside. That's like some work I did on the margin. Now back to this one. So the limit as x approaches infinity of tangent of this function, well, as the x's are getting bigger and bigger and bigger, we just observed that this inside function is approaching 0. All right? So as x's are approaching positive infinity, this inside function is approaching 0. So we're ending up with tangent of 0. So the whole thing is approaching tangent of 0. Tangent of 0 is 0. All right? And if you don't remember that, if that wasn't fast for you, that tangent of 0 is 0, please take a moment to think about why. All right, guys, we've got another one. Okay? So this is another situation where I have a composition of functions. I have 1 over x, that function, inside of e. So I'm going to do it again where I'm going off to the side. Okay, so I'm having this aside process. And I'm going to think about the limit as x approaches infinity of 1 over x. Guys, that again is 0. The numerator is staying 1. The denominator is growing huge. 0. So as x approaches infinity, this is approaching e to the 0 power. So this is approaching e to the 0 power, which is 1. All right? So the end behavior model works inside of other functions. Okay? And also, I want to say, before I tell you what the homework is, the end behavior model only works if x is approaching positive or negative infinity, and there is somewhere involved are powers of x. Okay, I hope that was clear, guys. If it's not, this is definitely something we can talk about tomorrow in class. Okay, the homework, this wasn't too bad of a video. It's only 13 minutes. Let me look at the homework. Okay, I'm going to cut it down a little bit. It's going to be page 13 all from the homework packet. Okay, so page 13 all. And guys, be aware, you can only use the end behavior model when x is approaching positive or negative infinity. I know I've said that like a million times, but it's important. There's a few of these where x is approaching like actual numbers. Okay, so you can't use the end behavior model for those. Alrighty, guys. I'll see you tomorrow. Bye-bye.